things you didn't, a few years ago, you wouldn't have thought that, that Python would have been involved in creating. So our next speaker is Alexis Lucattini. He's with the Australian Genome Research Facility. And when we first saw the topic for this talk, we were fascinated that Python was going to be involved. So I'm sure it'll be a really interesting talk. Please welcome Alexis.
Hey guys, I've created this using R, actually, just to stir things up a little bit. It works through a third party called Zeringan. So I have, and I've posted them to Twitter as well, so you should be able to see my Twitter account up there. And so if you press P, you'll enter the presentation notes and you'll see what I'm seeing here, or you'll see otherwise what's on the slides here. So yeah, my name's Alexis. I did my Bachelor of Biomedicine at Melbourne University. All my friends did med, didn't really think of that as an option, didn't get into med. Had a passion for computers, so went into Masters of Bioinformatics. We did a research component there where I worked at the AGRF on a little MinION, which is a DNA sequencer that I'll get into very shortly. And now I'm actually working at the Australian Genome Research Facility full-time, where I spend bit of that time also playing around with the MinION and also working through RNA-seq data and also debugging old Perl codes, which is so much fun, isn't it? So we're going to talk today about the MinION, not the one on the right here, but actually this little device here, which is a little DNA sequencer. DNA sequencers themselves are generally the size of massive computers, so we'll talk about that very soon. The complexities in base calling, so that's inferring the analog electrical data that you get off a MinION into CAGs and Ts that make up who we are. A very short introduction onto Fpgas. If you're here for the last talk, it's nothing like that at all. I really don't know much about Fpgas, and doing this, I still really don't. And we'll also talk about the paralleller board, which is this little device here. Similar to your little Pi boards as well. This one was created by Adaptiva in 2014. So first of all, the MinION, which I showed up before, it's the world's first portable DNA sequencer. It's gained a lot of traction, particularly on the Twitter sphere, the Internet of Things sphere, particularly because of its low capital cost and very easy library preparation. So preparing the DNA such that you can actually put it and load it onto this machine. People have done it on TED as well, where they've just grabbed a couple of pipettes and done it. And you can really, the library prep itself, all it requires is pipettes and a little micro spinnifuge to spin down liquids. It was founded by an ex-Illumina employee. Illumina are the main DNA sequencing facility gurus in the world. They own 90% of the share of the sequencing market. And they're not friends anymore. Anyway, we'll go like that. So how does this work? So at a very micro level here on the side, unfortunately, R doesn't like to embed videos too easily, so this is actually itself a link to another video. So at the micro level here, what we have is we have DNA, which is negatively charged, going from a negative, we have a voltage going, so it's wanting to go to the positive side, similar to maybe gel electrophoresis you might have done in high school. And as it goes through this pore, it creates, because it's negatively charged, it creates a current. And each nucleotide is slightly different in the way its chemical composition, and so each of them gives off a slightly different charge, as we see down here. It's not quite as simple as what we've got there, and we'll talk about that soon. But it does provide a few other benefits that other sequencing technologies do not. Exit. Oh, back. Okay. Cool. This is my first RStudio slide presentation as well. So the main benefits, the low capital cost, the fast library prep. It's portable as well, which is pretty cool. So this is founded by a group in Birmingham who are the real main frontiers of nanopore sequencing. So they went around Brazil during the Zika viral outbreak, tracking the Zika virus and the DNA and testing and seeing how quickly this virus is mutating. And that can answer questions down the line being like, is a vaccine going to be worth it, or is it going to be something like HIV where we'll never really be able to develop a vaccine because of its rate of mutations? So that was really cool, and that's something that could really only be done in real time with a Nanopore sequencer. But there are some huge limitations to this still. Compared to, say, Illumina, the accuracy of our base calling is only around about 85%. The yields of it are really, really low as well. I mean, you're not going to be able to cover, only now can we really start to cover a whole human genome, and only once. Illumina technology will easily do this 30 times or so for consensus and accuracy. That's really what we're after. So per yield as well, it's also very expensive. And as we'll discuss soon, the portability of it, this sequencing machine, isn't that useful at the moment. And the bioinformatics is still catching up. So the bioinformatics around this and analysing this data was always sort of focused on Illumina because that's all there was. And Illumina's reads are a bit shorter, but they're also much more accurate. And so I've put this picture here of a jigsaw puzzle. So when it comes to sort of assembling back a human genome, you have all these really short strings of DNA and you want to put them all together into these massive, the human genome is 3 gigabases. So it requires a lot of RAM and a lot of CPU power to put this all back together. But the MinION actually provides you long reads, so it's like having bigger jigsaw pieces, but they're a bit blurrier. So together with Illumina, you can actually be friends and you can actually have a decent quality genome. But the rebuttal to this is that this is significantly improving over time. So in my time in the wet lab, when I started back in early March and April last year, this was the yields that we were getting off this machine were next to nothing. This would look better, I think, as a logarithmic graph. And now we're getting up to around about 8 gigabases, so 2 to 3-fold coverage of a human genome. The limitations on portable sequencing are that, so Oxford Nanopore, they kind of remind me a bit like their CEO is a bit like Steve Jobs was. So, they come out with a new sort of chemistry and be like, this is the next big thing, even if it's just like a OS X 10.8 to 10.9 kind of thing. And you think, what are you talking about? And their designs as well, they're trying to really, I think, just be like the next Apple in this. And in that, particularly when they were pitching to the vendors, it was basically you'd prick yourself with some blood and you'd put it on a USB stick and it would do all the analysis for you. But unfortunately, what we've found is that the MinION really only focuses on one of these 3 things that you require for DNA sequencing. DNA itself is tightly wrapped up in our cells because it doesn't want to mutate and be affected by other things that could potentially cause it to change and then give us cancer or something. So it's quite hard to get DNA out of a cell to begin with. Sure, you can take it out into the middle of nowhere and stick a pet in it and get the DNA out, but you won't actually know what you've got until you go back to where your HPC is, so that you can then infer the squiggle data into CAGs and Ts, which is kind of frustrating yet. So, and really defeats the purpose of the portable sequencing. So first, we'll sort of go into about how actually this base calling works. So it's not. So this picture here that I'm trying to show here. Hang on, it's on this side. There we are. There's the mouse. So we say we've got maybe not be able to read this, but this spike here sort of corresponds to a G. But that's not really the case. What's actually going on is it's more representative of 5 or 6 nucleotides that are in the pore at any given moment, rather than 1. And so to infer then what's in there, you've got to use something like a hidden Markov model or now a recurrent neural network to take these sample points. And so you've got, say, 6 bases in there, and then they move out, and so these 5 bases become the position before it, and you've got a new base in. And so transferring from KMA, so if K represents 5 or K represents 6, and changing between those particular 2 states. So just as a refresher, here's a picture of a hidden Markov model, which you can find on Wikipedia. So we have in this situation, in the story of this one was that Alice and Bob were friends on the other side of the world, and Alice kind of knew where Bob lived and the states between rainy and sunny and the likelihood of changing between the 2, but she didn't know what any given day was. And when Bob would ring her up and tell her what he was doing that day, so Bob would either only be cleaning or only be shopping or only be walking. It wasn't really a fun person. So she would then try and infer whether or not it was rainy or whether or not it was sunny. So to her, the rainy and sunny are hidden. And so to us, we don't really know what particular state a is currently in the genome, but we do know when it changes and what that could mean about where it currently is, and you just sort of keep going along like that. So Alice would be stalkingly having a little note down, this is what he did today, what he did the day after, and trying to keep a record so that she can then infer whether or not it's rainy and sunny, and whether or not he will then is likely to go to walk to the shops tomorrow, or go for a walk, or go or clean before he tells her. It's the best I could do for an analogy there. So, but we've switched. It's switched to an RNN recently. RNN for a recurrent neural network, and in particular of an RNN and LSTM type. So RNN and HMMs, other than for these kind of weird examples, are used in speech recognition or in handwriting recognition, whether or not you're trying to determine whether or not whose handwriting it is, or whether or not you're trying to determine if that is this word that you could read in text, or if what they're saying, and then writing it down and like for closed captions purposes. But the LSTM in this can provide contextual-based information. So by sort of going through and back propagating through from before, where we've only got these two states for a hidden Markov model, we could then be like going back before, being like, was it sunny and rainy before that, and before that one, and before that one? But, so in the case of context-based speaking, we're talking about whether or not people were talking, say the word poor and poor, be it P-O-O-R or P-O-U-R, very hard to pick up and convert that to text when you don't know the context. And an LSTM seems to be quite good at doing that. So in these, and these seem to be quite more useful in terms of nanopore sequencing, because there seems to be things that are occurring much further later on, previously, that seem to be able to improve the accuracy of what's currently going through the particular nucleotide at that point. I'm not explaining that quite well, but maybe. So what I'm trying to point out is that this spike here that's corresponding to a G may also be related to something that's 10 or 12 bases back. But if our K-mer-based model is only on 5 on 6, then we're not going to be able to pick that up. So this is where the LSTM comes in quite handy. So I mentioned in my abstract that, so what's with the Fpga? So ONT, Oxford Nanopore Technologies, announced that they were looking into an Fpga in March 2017. And this was because previously what you would have to do was, once you had all your data off your MinION, you would send it up to the cloud. And this could potentially mean sending up 1 million files to an Amazon web server, waiting for them to finish and then downloading them again, which was exceptionally painful. And this was costing Oxford Nanopore around about $100,000 a month. So they scrapped that and said, you guys have to do the base calling yourselves, and they provided a CPU-based algorithm to do so. There's also a few open source algorithms that I'd recommend if you're interested in this kind of stuff, going through and contributing to. So it was quite, for us, where we've got one MinION and we have a whole bunch of HPCs, this was okay, because we could, in real time, be able to take the data off the MinION, run it through our HPCs. A few of my bioinformatic colleagues might get a bit annoyed because they're like, who's submitting all these jobs? But nonetheless, it was doable, but obviously not portable in this case. So where does that leave those trying the field sequencing applications? Well, they couldn't do it unless they had something like this little thing, which is currently in sort of the vaporware world, where the MinION would plug into an Fpga that would then plug into your laptop, where the Fpga had done all the base calling for you. And this is kind of where I thought, well, in my limited spare time, maybe I could try something and beat them to it. And having seen that the paralleller board that popped up on my newsfeed once contained an Fpga, I mean, how hard could this be? And I certainly don't regret creating this presentation and my investigations into this at all. I've learnt a lot, and I've learned a lot about parallel processing at the same time. So now we'll go into a little bit of an introduction on what FPGAs are. It stands for Field Programmable Gate Array, which sounds a bit like field-powered Gatorade, I think. So it's hopefully the lamest joke of today. If someone has a lamer joke, I don't want to hear it. But actually, so what is an FPGA? So kind of like, if you can remember back to either your introduction to engineering and stuff, you'll remember that you did and OR and NOT and NOR and NAND gates. And it's kind of a grid of those that are all sort of hardwired together to sort of mimic algorithmic logic that you've put in, that you've programmed it to be. So they're dynamic compared to, say, some other kind of hardware-based chips where you send it out and that's it. You can actually go back to an FPGA and you can actually reconfigure the logic, which is quite useful. And so you can have quite complex FPGAs will then have also little bits of RAM interlocked within them as well, so you can quickly go from having an object, putting it through somewhere in the FPGA and then outputting up to another piece of the FPGA, so you can jump through between CPU and FPGA quite easily. And it offers parallelization on a massive scale, and the reason this is because of the FPGA's clock ticks. So it kind of works FPGAs generally work between 10 megahertz and hundreds of megahertz in frequency. And so what a clock is doing is just oscillating between 0 and 1. And so in each of these logic blocks, they're going through each time the voltage is 0, they're doing nothing, and then when it flicks, they're going to be like, okay, so are the 0 and 1s together in the NAND gate will either go back to 0 during that microsecond, or if it's a 1 and 1 in the AND gate, it will go and decide to become a 1. And this offers parallelization at a massive scale because every single logic block is doing this at the same time within the FPGA itself. And they're quite an old technology, FPGAs. You know, they came around in the 80s, but they're still very useful and because they can do really specific tasks really, really quickly. And so they're used currently in the likes of video or imaging processing. So whether or not this is something where you've got a 360-degree camera on a GoPro and you just need to get it so that it provides an image for you to be able to look at, that you can look at visually. Whether or not it's signal processing is another example, or motor control is another example of that. And I've created some links in there. NASA also uses FPGAs in their bots and stuff that can travel on Mars and whatnot, which is pretty cool. And it also means that they can, because of the way that you can actually program an FPGA, it also means that they can then decide if there is a bug on their bot in Mars, that they can reprogram it. Not easily, but they do work for NASA, so I guess they know a thing or two about that kind of stuff. Because programming an FPGA is quite difficult. It's hardware programming, and as anyone who saw the talk just before would know, there's very few libraries available. It requires a different programming mindset from my limited experience working with VHDL or Verilog, where you need to be wary of this sort of clock cycle feature at the same time as wanting to try and implement your logic. There are I've had a look at a few, and as the talk before would say, now there's even a Python version of FPGA, that there are a few sort of C-based FPGA converters out there, C to FPGA converters out there now, that will allow you to do your FPGA programming in C. So having had a look at this, thinking maybe later I'll get back to this FPGA thing, I looked at the other component of the paralleller board, which is the Epiphany server. So the Epiphany component is Adaptiva's sort of equivalent processing unit of like an alternative to, say, Intel or NVIDIA for their CPUs. And this board's actually exceptionally efficient in the way it works because it's promoting, rather than having a couple of cores that have a lot of power, it's many cores that all have very little power. So this means that it's actually quite a bit more efficient because data's not having to run from the memory node on a CPU all the way over to the local RAM and back and forth. There's not too much of that talking because everything should be located within its own little block. But they can all talk to each other as well in case that your program is a bit too large and that you do need multiple nodes to do one particular thing. And it's highly scalable. We have what's here is a 64-bit processor. The paralleller board itself, the one that I got, is only 16. But nonetheless, you can actually program this to have up to 1 million different, if you have enough money, obviously, to stick these all things together, you can actually have it so that it's got 1 million cores, which is pretty amazing. I've never seen anyone do it, unfortunately. I've seen up to 4 or 5 of these all stacked up in a rack, and it looked pretty cool. So programming in the Epiphany is a bit different. It's using it's very similar to C. This is an Eclipse-based. They provide one with an Eclipse-based library, you could say. So when you start off your C project, Epiphany project, you'll say how many cores you'll specify the number of cores, number of rows in each core, number of columns in each core. Sorry, row number of the first core, column number of the second core, and this can all be determined quite easily by your Adaptiva software development kit. So depending on which type of board you've got, it'll tell you which one of these you need to enter. And programming it's very similar to C, but you have these sort of extra things like get core ID. Where's my mouse? Here, which will allow you to sort of set to a particular core, being like, I want you to do this. And I don't think Hello World is probably the best example for parallelization because it doesn't really make sense as a topic. Be like, yes, you can parallel Hello World from 12 different things, and it'll probably come back to you in the same time as just one did. But you're not really getting to test the compiler very well at all, test the server at all. So this is where ePython comes in, which is created by Nick Brown up in Edinburgh, which is an implementation of Python for the specifically for the Epiphany. So as we saw before, this is a prime number test. So we have 16 total cores, and we're testing each of them. So we're going to use core 1 to test number 1. We'll use core 2 to test number 2, etc., up to 16. And then we'll add on 16 here, so that core 1 will then test number 17, and core 2 will test number 18, and so on. And this is from a YouTube video that's also in my notes as well that you can check up. So interestingly though, the results of this was such that the Epiphany board itself was only ever so slightly faster than the ARM the ARM CPU that's also on this board to run Ubuntu and stuff which was a bit disappointing to see. And my tests of running an RNN on the ARM processor were that it was around about 2,000 times slower than I need it to be for it to be running in real time. So I could technically stack up 2,000 of these all in a row, but then I'd have something about the same size as our HPC, which was kind of defeating the purpose again. So I thought, well, why don't I sit on this? And because we've got coming up, announced by Adaptiva that they had a 1,024 core thing coming along, which would have been here, made the news headlines in the IT world back in October last year, which would have, and the Epiphany V stands for 5, not vaporware. That was just my little take on this. So unfortunately, the problem with this is that the main developer, Andreas Olofsson, has left Parallella to take up a job opportunity in DARPA, which I'm all happy for. I mean, imagine working in DARPA, that would be pretty amazing. And he's looking for someone to take it over because he reckons that if no one does, then this 1,024 core server, which will hopefully be the same size as this, will just remain forever as a prototype. So if you are looking at getting a new job and you like processing and I've inspired you enough on the Parallella board, then I would highly recommend that you do this. Because this would could potentially seriously speed things up as well, and we get to a point that maybe, hey, if we put 4 of these together, we have something that'll work with the MinIron in real time. And that's totally portable, stacking 4 of these on top. You can just throw that in your backpack, not in your pocket like this, but at least it's somewhat portable. So the things that I've learned in this project, that hobby boards are highly educational. Even if I haven't managed to get this project off the ground, I've learned so much about, first of all, setting up servers permissions. Root permissions, they're amazing, especially when you didn't have root permissions to begin with, which I do at work. But it's also given me like a much greater appreciation for systems administration teams, because they do actually do a lot of stuff that's not just installing packages for you, but they're actually hard monitoring servers and all the things. FPGAs are really hard to program. That's something else I learnt, but maybe I'll look at this new FPGA Python. But their importance in our day-to-day lives are quite underestimated. Just because they're an old technology, I don't think time is necessarily wasted in learning how to program these or learning how these work. And machine learning as well is something that's really worth investigating. It's not just a hype word anymore, so my little quote is learn it before it learns you. And I think that's all today. Do I not have a thing? Well, thank you very much for listening. That's our presentation.
Thanks very much. We've got time for a couple of quick questions. If anyone's got a question they'd like to ask.
David?
Oh.
Thank you. I was just wondering if you'd tried running this on the Intel Phi kind of co-processor, given it gives you something similar to this, a bunch of x86 processors.
Yeah, that's probably something I didn't mention. The reason that we need something out there is because you can run these particular RNNs on a laptop, but even like the i7 core laptops, like the powerful ones, will still take a week to run a 48-hour MinIron run, which is quite not.
Well, I mean, the Intel Phis are sort of like a GPU where they give you 64
Yeah.
100 cores
Okay.
or something like that.
Yeah.
And I don't know if they do a portable one, but I know NVIDIA do like a embedded kind of GPU
Okay.
sort of
Yeah.
product line now. So
Yeah, definitely. I know that. So the current algorithms developed by Oxford Nanopore are somewhat designed for CPUs. It would seem people that have tried them on GPUs have got different outputs.
yeah, the
than
Phi
those that
might
have
Phi
got
might work
CPUs,
well
which
then.
is- yeah.
The other thing is we've got at Melbourne Uni too. We've got access to the cloud FPGA instances if you want to have a play around with them. So, yeah.
Okay, be happy to.
When you
talk
get tired
later
of your little board or need more power or something like
Yeah.
that, although it's not portable, obviously.
Yeah.
Thanks.
Was there another question?
Yeah, just a couple.
So these boards have up to thousands of cores on a single die or single chip at least. Is that right? Or?
Yeah, the next version,
Okay,
if it gets
but-
off the ground, will. So this one's got 2 cores on the ARM processor and 16 on the Epiphany processor, the access through the FPGA itself.
And how you said it's an ARM core? Like what sort of ARM core is it? Sort of Cortex M0, Cortex M4? Like is it like floating point, relatively powerful? That sort of stuff?
Running these things, it's not. But I think it was an A9 or something, which reminded. But yeah, it's reasonably powerful, and there's no lag or anything running. Just running general Ubuntu on it. It seems quite good.
And how much benefit do you get from the fact that they're all interconnected in that fabric? How would an equivalent algorithm compare where you could just get 1,000 cloud cores or something like that?
Yeah, that's well, Parallella, it's like Adaptiva boasts that there's really no lag between having those nodes interconnected. So, but I haven't done a whole lot of testing on.
Right. So the algorithm is highly dependent on that reduced lag. Is that?
It would seem so, yeah.
So you described a little bit about the Nanospore.
The MinION thing?
Yep. That algorithm that does the converting to the CNG pairs, that's only the first stage. You've got then an algorithm later on that takes those sequences and converts it into like that jigsaw thing. What does that algorithm look like generally?
There's quite a few of those. It's not something that I tried on here, but it's definitely possible. People have really optimized those in the past few years to get them to be really quick. So they're often CPU based as well, but they're what's a good example? There's a lot of them that'll run things like hash tables and stuff against a genome, so it'll index the genome and run against those. So they've managed to make them powerful enough so that they're sort of proportional to the log size of the genome itself, in a way. As far as this goes, when it comes to the bottlenecks, it seems to be base calling and converting that analog signal into nucleotides rather than then converting and rather than trying to find where those nucleotides map to a genome.
Okay.
Look, that's probably all we've got time for question-wise. So please thank Alexis again. And in payment for your presentation,
Thank you very much. Yes.
There's